Thanks, David. At this stage, we have very nice, I would say, six topics, six papers that we will listen to, and feel free to ask any questions in the chat box, and we'll have some time for question and answers. The first presentation, actually, the authors couldn't make it due to some trips that they're making at the moment. So they shared the video recording of their presentation. So I
Yeah.
asked the coordinator to share the video, play it, and then you'll have some time. I think I need to double check if we have any of the co-authors present here for any questions following the recording.
Yeah, I'm ready to play the video.
Yikan, please. Yes,
Yeah,
please.
sure. Uh, Sorry, but uh, um, can you hear the voice?
Not yet.
Okay.
You can just take share sound when you are sharing your screen. So unshare your screen, and then when you are sharing your screen, just take share sounds.
Okay, I saw it. Thanks for that. Sure. Sound. Cool.
Hi everyone, I'm pleased to present our research on a graph-based framework for optimizing multi-scale
Yeah, it
ride
works.
matching problems in peer-to-peer ride-sharing systems. Today, I will be discussing our approach to improving peer-to-peer ride-sharing by introducing a novel graph-based optimization method. Let's begin with some background. Ride-sharing, powered by platforms like Uber and Lyft, has revolutionized on-demand transport. However, it has also contributed to challenges such as increases vehicle mile travel, congestions, and deadheading, where drivers travel without passengers. Peer-to-peer ride-sharing, where drivers and riders share trips, has emerged as a more sustainable solution. Unlike commercial ride-sharing, which is profit-driven, peer-to-peer ride-sharing is typically cost-sharing, with drivers and riders saving on travel expenses. This system reduced the number of vehicles on the road, thereby minimizing traffic congestion and VMT, eventually contributing to a more sustainable transportation model. Graph-based methods offer a robust framework for solving ride matching problems. In a graph, participants are represented as nodes, and potential ride-sharing matches form the edges. A common approach uses Viper-type graph, where riders and drivers are a separate set of nodes. However, these methods work well for one-to-one matches. For example, one rider paired with one driver. As we extended to more complex situations, such as one driver picking up multiple riders or riders transferring between drivers, the problem becomes computationally challenging. In graph terms, when we allow one-to-many or many-to-many relationship, the graph is no longer a simple Viper-type structure. We have to consider grouping of riders and drivers as potential matches. This dramatically increases the number of possible combinations and edges in the graph. Hence, scaling up to multi-riders or multi-op scenario introduces substantial complexity. So our approach introduced a graph-based optimization framework capable of handling various ride matching configuration, one-to-one, one-to-many, and many-to-many cases. The goal is to maximize the system-wide benefits in terms of cost or distance saved. Key components of the framework include a novel graph representation with spatial transhuman node for handling multi-hop, multiple rider matches, a pre-processing step to filter out infeasible matches, reducing complexity. A cost-saving function that quantifies the benefit of sharing ride. Linear programming optimization to select the optimal set of matches that maximize cost saving. Validation through simulations comparing the proposed method with existing real-time matching heuristics. Traditional bipartite matching works for simple one-to-one matches, but fails in more complex scenarios. For example, as shown in the left figure, imagine a rider who cannot reach their destination with the single drivers and instead needs two drivers sequentially. In a standard bipartite graph, these rider nodes might connect to each driver individually, but the graph cannot properly ensure that the rider is matched to both drivers together. The rider could be mistakenly matched to only one driver or two on incompatible combination. In our paper, we give a concrete illustration, such as rider 1 has two feasible driver groups to get to destination, which is set number 1 include driver 1 and 2, and set number 2 which includes driver 3 and 4. Let us assume that the best option is set number 1 with driver 1 and 2 together, but a naive approach might assign rider 1 to just driver 1 or to driver 1 and driver 3, which is infeasible because no single driver in those incorrect pairing can cover the whole trips. In contrast, our approaches use a transhuman node to model this grouping. The rider is connected to transhuman node that represent feasible driver groups, ensuring that only valid driver sets are considered. This method effectively handles both one-to-many and many-to-many matchings, unlike traditional bipartite graph. This slide illustrates our methodology. The process starts with defining the peer-to-peer ride matching problem, followed by a pre-processing phase that filters infeasible matches. We then generate feasible driver-rider matching set, calculate cost saving for each, and build a ride matching graph. The linear program solver is then applied to find the optimal matching solution. This framework ensures that matching process is both efficient and computationally feasible. So here we explore different strategies for filtering infeasible matches and improving efficiency. First of all, route-based matching is considered only if a driver's shortest path can accommodate picking up of riders whose origin and destination lie along that route. The advantage of this approach is that it's computationally simple. It's easy to check if a rider's trip is on a driver's route. However, it's also quite restrictive. By requiring the exact shortest path overlap, we end up discarding many possibility matches. It leads to a lower matching rate because real people might be willing to take minor detour to pick someone up, but the strict route-based method wouldn't allow that. In other words, it reduces feasible match opportunities by enforcing a very rigid criterion. So we adopt a network-based approach proposed by Neda and Jayakrishnan's 2017 work. This road network-based method expands the matching area by considering the road network within a certain time and distance constraint and significantly increasing feasible matches while keeping computational manageable. We also imposed a transfer limit, for example, 1 or 2 transfer, to ensure practical matching. This prevents overly complex route that would be inconvenient for riders and reduce computationally complexity by limiting possible matches. Algorithm 1 shows how we generate the peer-to-peer ride matching network from the feasible set of matches in pseudocode form. Let me explain this algorithm in a more narrative way as if walking through it. The goal of algorithm 1 is to construct the edge of our peer-to-peer ride matching network given the feasible pre-match set we identified. The input to this algorithm include the list of rider nodes and driver nodes and the list of pre-match set, which are the set of driver feasible for each rider. The output will be the complete peer-to-peer ride matching network graph ready for the linear programming solver. For each rider, create edges to spatial transhumant node, each representing one possible way the rider can ride share. Assign a cost saving to each of those possibilities. Then connect those transhumant nodes to the specific drivers involved in that possibility. The result is a network where any valid flow from a rider through a transhumant node to some drivers corresponding to a feasible rideshare assignment for that riders and those drivers. After running this algorithm for all riders, we have the full peer-to-peer ride matching graph. This graph is ready for the optimization step, containing all the riders, transhumant, driver edges, properly weighed and constrained. This slide discusses the structure of the peer-to-peer ride matching graph and the cost-saving function. The network acts as a flow problem, include riders act as a supply node, driver act as demand node, and transhumant node connect riders and driver. The cost-saving function calculates the distance saved by ride sharing, comparing individual trips to shared trip. The edge weights represent the benefit of sharing a ride, and negative cost edges are discarded. The optimization then seeks to maximize cost saving by selecting the best matchings. On this slide, we present the linear program formulation of ride matching problem. The object is to maximize the total cost saving while ensuring that each rider is matched to exactly one transhumant node and each driver serves at most one driver. The LP solver efficiently identifies the optimal matching solution by respecting this constraint. In the extended framework for many-to-many matchings, we introduce sharing nodes to allow a single driver to pick up multiple riders. These sharing nodes collect flow from several riders before connecting to a driver. We also account for vehicle capacity constraint to ensure that a driver car can only carry a limited number of passengers. These extensions allow for more efficient matching in scenarios with high demand. Linear programming formulation for many-to-many matching incorporates this capacity constraint. The object remains to maximize cost saving, but now the constraint also ensures that the total flow into a driver does not exceed the vehicle's capacity. In our computational experiments, we applied the model to a real-world scenario in Irvine, California. Using the California statewide transportation demand model, we simulated a small-scale peer-to-peer ride-sharing system with 3,000 participants. Various vehicle classes and costs were incorporated to reflect realistic operating conditions. We now examine the relationship between the number of drivers and cost saving. By varying the number of drivers from 6,000 to 12,000, while keeping the number of riders constant at 6,000. We observed that increasing the number of drivers results in higher cost saving. The market hub single rider scenario achieved greater saving compared to the single hub scenario, highlighting the importance of transfer in maximizing efficiency. This slide summarizes the different scenarios tested in our analysis. We gradually allow more complexity by introducing transfers and carpooling. These scenarios enable us to analyze how features like transfer limits and carpool size contribute to system performance. Hence, we compare the performance of each scenario. The number of served riders increases as we relax transfer, and carpooling constraint. However, as complexity grows, so does computational time, especially when many transfers are allowed. The trade-off between match quality and computational efficiency is an important consideration in real-world applications. We compare the LP-based optimization matching method with a real-time matching algorithm across all scenarios. In every scenario, the LP method achieves higher cost savings. The difference is particularly significant in more complex scenarios, where the real-time algorithm misses opportunity that the LP method captures. Computational time for each scenario are shown here. For simpler one-to-one matching, computational time remained constant, but once transfers are introduced, time increases significantly due to the complexity of managing transshipment node. The many-to-many matching scenario incurs the highest computational time, but it provides the greatest benefit in terms of cost savings. Finally, this figure illustrates the number of matched riders across different problem size and ride matching scenarios. In many-to-many matching, the gap between rider and required driver narrows as rider demand increases, showing the benefit of carpooling and multi-home matching. Thank you for your time and attention.
Brilliant. So if you have questions for the authors, I don't see them among the attendees. So I would say I encourage you to reach out to them directly and email them and ask your questions. Without further delay, I would like to jump to the next presentation. Predicting driver retention in ride-hailing services, a study on the influence of socio-demographic behavioral factors. And I believe Taufik is with us. Taufik, if you can share your screen, and the floor is yours.
Yeah, I will stop sharing mine this at the time. I will ask Taufik to unmute himself.
Taufik, can you confirm your, okay.
And now it's me, sorry.
No, can you confirm, Taufik, if you're with us?
Yeah, I sent him the message, but he didn't reply yet.
Anybody else from the team is here in the room who wants to start the presentation? Can we then proceed with the recording if there is an uploaded? Because Tawfiq confirmed that he'll be the presenter.
Yes, and he is actually in the room. Let me find if
I can't find him.
it seems like they didn't upload the recording
All right.
as well. So
So maybe what I can do, we can jump to the third presentation to save time here. The topic is differentiated service pricing strategies for ride hailing, considering rational, inattentive passengers. And I think Chuanling confirmed to be the presenter.
yeah, okay.
Yes, please go ahead. Floor is yours. Looking forward to listening to your presentation. Thanks.
Good afternoon, distinguished experts and scholars. I'm Zhang Hui from the University of Civil Engineering and Architecture under the supervision of Professor Chuanling Zhao. Today, I'm honored to present my research title, Differentiate Service Pricing Strategy for Ride-Hailing Considering Rational, Inattentive Passenger. The emergency of ride-hailing service has not only effectively met passenger travel demands and significantly improved their travel convenience, but also complement and enhance the traditional taxi service, forming a new flexible mode of urban transportation. Among the many topics in this field, pricing strategy for ride-hailing platform has emerged as one of the most intriguing and essential areas of study. On the right side of the slide, I show the two screenshots from a popular ride-hailing app. This reflects a key real-world phenomenon. Passengers make choice among differentiated service based on their preference. Thus, how platforms should design and optimize differentiated price strategy becomes a critical research question. Further, from passenger perspective, we observe that they often lack complete information about the true quality of service. To capture this behavioral feature, our study incorporates the concept of rationality in attentive passenger, accounting for their limited information processing capacity and decision-making under the cognitive constraint. Let me first direct your attention to triangular diagram on the left. It outlines the entire structure of information and monetary flow within a monopolist ride-hailing platform represented at the top vertex and its interaction with rationality in attentive passenger and ride-hailing drivers represented at the two lower vertices. The platform strategy manipulation of these three elements ultimately shaped the outcome we aim to study, whether it profit maximization or self-aware maximization. To simulate our research within the broader academic context, we review prior literature on the ride-hailing price strategy and summarize three main standards of work. First, several research explore ride-hailing price from perspective of passenger choice behavior and its underlying psychology mechanism. Some scholars have added the concept of rationality to price of ride-hailing. In 2022, Wang addressed its issue of heterogeneous preference among both passengers and drivers for different service tiers, and modeled the joint model choice behavior from both sides of the platform. Building upon this prior study, we distill the following core question. Under the rational inattention and coexistence of high and lower quality service, how should the platform jointly the price and commission to optimize either profit or social welfare? To address the research question, we construct a mathematical model to analyze and solve the problem systematically. Here are the key parameters involved our model. The most important is passenger perceived quality, perceived service state, and unit information cost. Now, let me introduce the core part of our model. Starting from the left side of the diagram, we define three distinct platform strategies. The first strategy is to offer both high and low quality ride-hailing service. The second is to offer only low quality service, and the third is to offer only high quality service. Based on the three settings, we construct a B-level optimization model, in which the red box on the left represents the lower level model, while the red box on the right denotes the upper level model. In the lower level model, we incorporate a two-side user equilibrium framework. From the passenger side, we model rational inattentive passenger and introduce a key variable, WJC, representing the expected waiting time for passenger through serve J. The utility function, denoted as U, captures the passenger's benefit from selecting service J, given their subjective perception of service quality, denotes H and L for high and low quality representative. The joint perceived serve state following a probability density that is the product of the individual density function of high and low perceived quality. We then employ a general multimodal model to determine the condition choice probability of selecting survey under the composite perception state H and L. Lastly, we drive the unconditioned choice probability by integrating over all possible perception state. From this formulation, we can determine the passenger side demands for each survey type. On the driver side, we assume that drivers are fully rationed. Their supply decision are driven in parallel structure, responding to commission matching expectation and server performance. With both passenger demand and driver supply qualified, we then model the matching process between them using a Cobb-Douglas production function, which captures the complementary and diminishing returns between the numbers of passenger and available driver. Moving to the red box on the far right, this part represents the upper level model, which contains two alternative optimization objectives: maximization of platform profit and maximization of social welfare. In terms of computation, this is the B-level optimization problem, which is anti-hard in nature. Taking strategy 1, the differentiated serve market at an example, we adopt a heuristic algorithm that combines the partial swarm optimization algorithm with method of the successive average. This approach following the methodology proposed by Challenger, which allows us to efficiently approximate the optimal solution under the high dimension and non-convex conditions. Finally, we conduct a numerical experiment to validate the proposed model and algorithm. As shown in the table on the left, we input relevant model parameters, including latent travel demand, latent service supply, passengers unit value of waiting time for both high quality survey and low quality survey, driver uniting value of waiting time for survey high and low, representative, and the passenger perceived survey quality state, which is assumed to following a uniform distribution over a specified interval. In the line chart on the left, we illustrate the evolution of platforms profit under the strategy 1 as the number of interactions increase. As shown in both platform profit and social welfare across the three strategies tend to stabilize around the 13th interaction, demonstrating a good convergence and computation efficiency of our solution algorithm. On the table to the right, we summarize the optimal results under the two objectives: platform profit maximization and social welfare maximization for three serve strategies. When the objective is profit maximization, the platform achieved the highest profit under strategy 3, where only high quality survey is offered in construct. When the objective is social welfare maximization, the platform should adopt strategy 1, offer both high and low quality surveys simultaneously. Next, we conduct a sensitive analysis with respect to the unit information cost. Let's first look at the figure on the left. The solid line represents objective 1, platform profit maximization, while the dashed line corresponds to objective 2, social welfare maximization. From the perspective of profit maximization, we observe that Under three-served strategy, platform profit first increase and then decrease at uniting information cost rate. When the information cost is low, the platform can efficiently coverage serve differentiate to passenger, allowed for better price leverage and high profit. However, the information cost increase, passenger face greater difficulty in acquiring and processing survey-related information. This weakens the platform's pricing power and leading to overall decline to profitability. In construct, under the social welfare maximization objective, social welfare consistently decline and information cost increase across all strategies. This because high information cost reduce passenger ability to distinguish between survey quality, which hampers efficient passenger-driver matching, utility lowering the overall resource allocation efficiency of system. Now turning to the figure on the right, we examine the matching rate under the social welfare objective dashed line. It shows a relatively stable overall matching performance, but with distinct pattern. The matching rate for high-quality survey remains consistently low and near unchanged, while the matching rate for low-quality survey stayed consistently higher. This indicates that when optimizing for social welfare, the platform tends to prioritize the accessibility and based travel need for majority of users, rather than focus on allocating results to premium survey. In other words, the system favor broader serve coverage over selective high-end matching, thereby improving inclusive access to ride-hailing. As shown in the left figure, with the increase of uniform information cost, there exists a threshold of unit information cost for all three strategies where the change of survey price and commission rate show opposite trends. Under strategy 1, the price gap between survey high and low widen first, then narrow, while the commission gap narrow first and widen as unit information cost increase. A similar pattern is observed under the strategy 2 and 3. Under the objective 2, namely social welfare maximization, the price and commission outcome display distinct pattern across strategy as shown in the figure on the right. An important observation is that under strategy 1, the platform set a price of high-quality survey to 0, while maintaining a relative high price for low-quality survey. At the same time, it offers a low commission rate to drivers of survey. This configuration balances the incentive and ensures that social welfare is a mechanism that displays increasing information friction in the system. Under objective 1, as shown in the left figure, the supply and demand dynamic vary significantly, vary increasing unit information cost. Under the strategy 1, supply and the demand for high survey decline, then rise, while a low survey they rise, then decline. It is worth noting that when the information cost is high, even though price decreasing and the commission rate slightly increasing in strategy 2 and 3, the growing information barrier prevent passenger from accurately evaluating survey quality, which in turn reduce their willingness to use ride-hailing survey. This leads to demand slight decline, long matching time, and an eventual reverse in initial growth of supply, resulting in an overall decline in both supply and demand under these two strategies. In conclusion, our study provides a structured framework for analysis, differentiate survey pricing strategy in ride-hailing platform considering passenger behavior under rational inattention. The modeling capture how pricing and commission design influence platform performance under different objective and review key interaction between server type information friction and market outcomes. About future work could employ the following direction. First, real-world driver may also explain the rational intention, incorporating of multiple differentiated survey model, consideration of spiritual characteristic of ride-hailing market, reduction of uniform priority brief assumption for passenger. That's all. Thank you.
Thank you very much, Hoi. I don't see any questions for the authors. If there is any questions, we might have time for one quick question. And in the meantime, waiting for anybody to share their questions, can we check again? I believe we have one of the co-authors of the second presentation now with us.
Yes, should be.
Surav,
Yep.
Surav, are you ready to start your presentation?
Yes, I'm ready. I'm sharing my screen now.
Brilliant. Thank you, Hoi, for your great presentation. It was very interesting and well explained. Let's move back to the second presentation, Predicting Driver Retention in Ride-Hailing Services, a study on the influence of socio-demographic and behavioral factors. Surav, floor is yours. We can't hear you.
Thank you, Dr. Rashidi.
Yes,
Good
go ahead.
afternoon, everyone. Thank you for joining me today. I'm Saurabh, and I'll be presenting findings from our research titled Predicting Driver Retention in Ride-Hailing Platforms, an empirical study of socio-demographic and behavioral influences. The other authors of the paper are Saurabh Sarkar, Chandrasekhar Mondal, and the corresponding author is Dr. M.D. Tawfiq Sarar. This study examines why some drivers continue in the profession while others drop out, with a focus on socio-economic, demographic, and environmental factors. Okay, let's just begin with some background. Ride-hailing services have significantly transformed urban transportation, particularly by providing flexible and time-effective mobility options. In cities like Dhaka, where public transit is limited and traffic congestion is severe, these services have emerged as a vital alternative for daily commuting. Ride-sharing platforms such as Uber, Pathao, and Ovai have not only reshaped how people moved around the city, but also created substantial employment opportunities for drivers. However, despite the early growth and popularity of these platforms, many ride-hailing companies in Dhaka have struggled to sustain their operations, highlighting the volatility of this market. One of the key factors influencing the instability is driver retention. Ensuring that drivers remain engaged and committed to these platforms is essential for long-term sustainability of the ride-hailing as a transportation solution in Dhaka. Despite the initial boom in ride-hailing services in Dhaka, out of 15 registered platforms in 2018, only 3 are now in service. One major issue that drivers frequently turn to off-app services, providing rides outside the official platforms to boost their income. While this helps them financially, it undermines both platform revenue and user trust. Additionally, high operational cost, chronic traffic congestion, and a lack of clear regulatory frameworks further erode driver satisfaction. These factors often lead to high driver turnover, threatening the sustainability of the entire sector. What complicates the situation even more is the limited research available on why drivers choose to stay with or leave a platform, especially in developing urban contexts like Dhaka. Understanding these decisions is critical. Without it, the industry remains fragile and ill-equipped to support long-term sustainable growth. The primary objective of this research is to investigate the various factors that influence ride-hailing driver retention in Dhaka, focusing specifically on socioeconomic, behavioral, and environmental dimensions. We examine how variables such as education level, marital status, driving experience, vehicle ownership, perceived road comfort, and involvement in op-app services affect a driver decisions to remain in the ride-hailing sector. To analyze this relationship, we apply an ordered logistic regression model. This approach helps us to quantify how each factor contributes to the likelihood of a driver continuing with the platform-based service. Our goal is twofold. First, to provide actionable insights for policymakers to address issues like traffic congestion and inadequate infrastructure. And second, to offer targeted recommendations for ride-hailing platforms to improve driver satisfaction, reduce op-app practices, and ultimately support a more stable industry. To explore the factors influencing driver retention, we conducted a structured survey using face-to-face interviews with professional ride-hailing drivers in Dhaka. The data collection took place over a 4-month period from August to November 2023, ensuring enough time to capture a diverse and representative sample. In total, we gathered responses from 401 ride-hailing drivers. The survey focused on several key areas like driver experience and behavior, built environmental preference, vehicle type and ownership, and their socio-demographic characteristics. To analyze the factors influencing driver retention, we employed an ordered logistic regression model. This method was chosen because our dependent variable is ordinal in nature. We considered our models like multinomial, other models like multinomial logistic regression, probit, and linear models, but the ordered logistic approaches provided a better fit for handling ordered categorical data and preserving the structure of the outcome variable. Our dependent variable was drivers' stated likelihood of continuing in the profession, categorized as unlikely, somewhat likely, and very likely. From the drivers who are sure that they do not want to stay in the sector, they responded unlikely, and who are not sure currently, but there is a probability they will continue, they responded somewhat likely, and the drivers were sure they will continue in this sector in the future, they responded very likely. For independent variable section, we first conducted a chi-square test with a significance threshold of 0.05 to screen for relevant factors, and only variables that are statistically significant were retained in the final regression model. Let me now show a brief overview of the driver demographics in our study. The sample reflects a young and diverse group. About 26% of drivers were aged 18 to 25, and 28% were between 26 and 35. Around 68% worked full-time. In terms of education, 36% had completed undergraduate studies, while 17% had only primary education. Nearly half of the drivers came from suburban areas, and just 10% were raised in Dhaka city. Around 2/3 were married. Finally, when it comes to experience, 28% had been driving for 1 to 2 years, and another 28% for 2 to 3 years, indicating a moderately experienced workforce. Looking at operational data, 79% of drivers owned their vehicles, while 21% rented. Vehicle types included 47% motorcycles, 27% cars, and 26% CNGs, which is actually a three-wheeler, a common sight on Dhaka City Road. In the past 30 days, 53% completed 100 to 200 trips, 28% did fewer than 100, and only 19% did over 200 trips. Traffic congestion had a strong impact, with 85% saying it affects their driving decision, and 44% strongly emphasizing the importance of waiting times. The table shows list of variables that we have found significant in our study. We also calculate the odds ratio to better compare between variables and understand its impact. Our analysis revealed several key factors influencing driver retention in Dhaka's ride-hailing sector. First, education plays a significant role. Drivers with secondary or higher education are much less likely to continue working in the ride-hailing sector. This is likely because they have access to alternative employment opportunities. Interestingly, drivers who were raised in Dhaka itself are less likely to stay in the sector compared to those from rural areas. This may reflect greater job options available within the city. Experience matters greatly as well. Drivers with more than 3 years of experience are an astonishingly 90 times more likely to continue, highlighting the importance of familiarity and the stability in the job. In addition, vehicle ownership influences retention. Drivers who rent their vehicles are 7.6 times more likely to continue compared to owner drivers. This may suggest that owner drivers often treat ride-hailing as a secondary source of income, while renters rely on it as their primary source of livelihood. Continuing with the key findings, vehicle type also plays an important role. Driver using private cars and CNG, which is a three-wheeler, are about 4 times more likely to continue compared to motorbike drivers. This may be linked to higher fares and better earning potential with these vehicle types. Conversely, drivers comfortable navigating mixed traffic conditions with pedestrians and non-motorized vehicles are 94 times more likely to stay in the sector. This clearly reflects the unique and complex traffic environment of Dhaka. When it comes to the road comfort, we see some interesting patterns. Drivers who feel comfortable driving on roads with dividers are less likely to continue, which could be due to the traffic congestion and delays often found on such roads. Traffic congestion emerges as a major barrier. Drivers who perceive congestion as significantly impacting their work are much less likely to continue. Similarly, drivers frustrated by long waiting times also tend to leave, underscoring how inefficiencies and income instability drive slow destruction in the industry. To assess the performance and reliability of our ordered logistic regression model, we examined several key indicators. First, the pseudo R-square values suggest a strong explanatory power, indicating that the model effectively captures the relationship between predictors and the outcome variables, as all the values are over 0.75. In terms of predictive performance, we conducted a confusion matrix analysis, which revealed a high level of classification accuracy across categories, which is over 80%. Looking at precision by class, we achieved almost same results, a macro average precision of 90% and a weighted average precision of 91%. These results indicating a balanced classification performance across all three categories with no substantial bias towards any single class. To conclude, our research highlights several key insights into driver retention with the ride-hailing platforms. First, we found that drivers with higher levels of education, those from urban backgrounds, and those using private vehicles are significantly less likely to continue driving on these platforms. In contrast, more experienced drivers, those using rental vehicles and those operating cars or CNGs, tends to have higher retention rates. Importantly, drivers' comfort with navigating mixed traffic roads and handling congestions directly influences their job satisfaction and their decision to continue. Traffic congestion and prolonged waiting times emerge as a major deterrents, negatively impacting driver retention. Lastly, we also observed that inefficient ride dispatching system disproportionately affect newer and less experienced drivers, making it harder for them to sustain their engagement with the platforms. Based on our findings, several policy recommendations emerged to improve driver retention and overall ride-hailing service quality. Key policy measures to improve driver retention include enhancing infrastructure and congestion management and addressing informal ride-hailing practices to ensure fairness. Investing in driver training will improve safety and satisfaction, while incentives for safer driving in low-demand areas can help balance supply and demand. Lastly, the findings suggest strategic collaboration between ride-hailing platforms and urban transport authorities that could significantly improve routing, reduce waiting time, and ultimately driver retention. Now, the limitations and future research. While this study offers valuable insights, it is important to acknowledge certain limitations. First, the research is geographically limited to Dhaka, which may affect the generalizability of the findings to other cities or regions with different traffic conditions and socio-economic context. Second, our reliance on self-reported data introduces the potential for bias, as responses may be influenced by personal perceptions or inaccuracies in recall. Additionally, the cross-sectional nature of the data provides only a snapshot of drivers' decisions at a single point in time, limiting our ability to capture their behavioral change over time. Finally, there are also unmeasured factors that could influence driver retention, such as personal health and income levels, which were not fully accounted for this study. Looking ahead, there are several promising directions for future research. First, conducting comparative studies across different cities with varying traffic patterns and infrastructure will help us understand how local contexts influence driver retention and satisfaction. Second, the implementing longitudinal research designs would allow us to track drivers' experience and retention trends over time, providing a deeper insights into causal relationship and long-term effects. Lastly, exploring the physiological impacts of ride-hailing work on drivers such as stress, fatigue, and overall health would reveal important factors affecting their well-being and job continuation. This is all from my presentation today. Thank you everyone for your time and attention. And I'm happy to take any questions or hear your thoughts on our research.
Thank you very much, Saurabh. Very clear presentation and perfect on timing. We have time if there is any questions. I don't see anything in the chat box. I just have a quick question for you. Did you ask these drivers where they go to if they want to change or they don't stay with the ride hailing service? What other sectors they go to if they don't stay?
No, thank you for your question, Dr. Rashidi. But we didn't ask that question to the drivers who actually participated in our survey. But as in our survey, we showed a trend that with higher education, they tend to leave the platforms. So I think they move towards more professional job or desk job after leaving that, and a substantial percentage of the drivers are doing it for the part-time. So maybe they're doing it for some earning some quick cash, but after they have completed their study, they will likely move forward doing a bit better jobs than ride sharing.
Brilliant. Thank you very much. I would say still as we switch to the next presentation, if there is any other questions, please share it in the chat box. The next presentation titled Factors and Barriers for Peer-to-Peer Car Sharing Adoption in Greece. I don't see any of the authors actually in the room. Can you confirm if, or maybe in the chat box, any of the authors in? And I didn't receive any confirmation from them sharing with us who will be the presenter. Yikon, do we have a video?
Yep, yeah, as you can see,
Oh,
there's
brilliant.
a
Yes,
video.
you're right. Brilliant. So let's play the video then.
Sure,
Thank you.
sure. Let me check the.
Hello, my name is Christos Karolemeas.
Yes, we can hear it. Thanks.
The sound is a little bit low, right? I think. Let me.
Hello, my name is Christos Karolemeas, and on
Sure.
behalf of all the authors, I will present you our study, Factors and Barriers for Peer-to-Peer Car Sharing Adoption in Greece. The rapid increase in private car use worldwide and in Greek cities has led to severe traffic congestion, extended commute times, increased stress, lack of parking, and increasing pollution in air and noise pollution. Limited investment in efficient public transportation, coupled with all planning mistakes, increased car dependency in Greece and overburdened municipal resources and public infrastructure. Greece's introduction of SAMs within the EU framework promotes greener transportation and shared mobility to reduce congestion and pollution and improve the quality of life in cities. Conventional car sharing, fleets available on demand, has the potential to reduce individual car ownership and fill gaps between the use of private vehicles and public transport. Although peer-to-peer car sharing could optimize existing vehicle use in Greece, previous initiatives have not reached critical mass. This study examines the level of awareness, demographic and behavioral factors, technological and regulatory barriers, and perceived risks and benefits. There are 4 primary car sharing models: business to consumer, business to government, business to business, and peer-to-peer, where peer-to-peer car sharing uniquely enables private individuals to rent out personal vehicles via digital platforms, creating a decentralized sharing economy. Unlike ride-sharing, peer-to-peer users drive owner-operated vehicles, leveraging idle cars without major infrastructure investments. Leading services include Turo, which operates both in US, Canada, United Kingdom and Germany, Getaround, which operates in US and Europe, Snapcar, which operate mainly in the Netherlands, and Hirecar, which targets rideshare drivers. Financial incentives, environmental benefits, and trust-building mechanisms drive uptake, while regulatory fragmentation, insurance complexity, and cultural reluctance pose challenges. Despite global insights, empirical studies on peer-to-peer car sharing in Greece are lacking. Existing work focuses on traditional schemes, highlighting the need for targeted research on peer-to-peer perception and infrastructural barriers. Regarding the methodology, we use the structured questionnaire with closed-ended Likert questions, pilot-tested and refined for clarity, then delivered via a digital platform to minimize bias. We recruited 203 urban Greek residents between 18 and 65 years through academic and social networks, ensuring demographic diversity despite inherent sampling limitations. We collected data on socio-demographics, travel behavior, technology familiarity, peer-to-peer usage intent, both as owners and renters, and perceived barriers and incentives. We employed descriptive statistics and inferential tests to explore adoption factors. The participation in the surveys was voluntary, and the responses were completely anonymous. We follow the GDPR guidelines as well as the NTUA Ethics Committee guidelines. In terms of demographics, approximately 53% were women and 47% were men. We have a similar representation in the 26-35 age group and in the 46-55 age group. Almost 78% hold at least a university degree, either bachelor or master. Most of the respondents were also employed in the private sector, comprising the largest occupational group, around 38%. Finally, over 90% own a private car, 67% have constant household vehicle access. However, almost 60% are unfamiliar with peer-to-peer car sharing. Regarding factors influencing car sharing adoption, respondents heavily rely on smartphones and Google Maps, whereas computers, telematics, and taxi apps see infrequent use for digital trip planning tools. For the key adoption drivers, economic benefit and vehicle cleanliness top the list, closely followed by free parking, vehicle availability, and ease of use. For the lower priority features, variety of vehicle types and electric vehicle options generate only moderate to low enthusiasm, while comfort and eco-friendliness occupy the mid-range. A car is seen as necessary and a source of freedom and flexibility, yet viewed as little social status emblem. The above show us that there is a strong preference for cost savings, convenience, and hygiene, which suggests that platforms should prioritize affordability, booking simplicity, and well-maintained vehicles. In terms of willingness to participate in peer-to-peer car sharing schemes, for car owners, economic benefit is the dominant incentive. On the other hand, lack of trust in other users, vehicle wear and tear and mechanical breakdown, and insurance and liability worries are major deterrents. Provision of full coverage insurance, flexibility to site availability, and the ability to approve renters are critical enablers. Control over pricing and automated handovers also matter. Fewer than 25% of owners express a clear willingness, very interested or extremely interested, to rent out their vehicle, while nearly 47% lean against participation. Regarding renters, cost savings and immediate vehicle availability drive their interest, while they worry about vehicle condition, availability scarcity, and owner reliability. Renters insist on full insurance coverage and transparent rental terms. Two ordinal regression models were developed to predict willingness to participate both as renter and as car owner. For the car owner's model, economic benefit and environmental concern increases willingness, while on the other hand, vehicle wear and tear and renter approval requirement decrease it. For the renter's model, immediate vehicle availability and perceived economic benefit boost willingness, while safety toward owners and hiring complexity deter participation. In conclusion, our findings demonstrate that economic consideration and trust-related safeguards are the decisive factors shaping both car owners and renters' decisions to participate in peer-to-peer car sharing. Owners are motivated primarily by the prospect of covering maintenance, insurance, and depreciation costs, yet their willingness is significantly dampened by concerns over wear and tear, misuse, and liability. Similarly, prospective renters place the highest values on cost savings and immediate vehicle availability, but they remain wary of vehicle condition and personal safety when interacting with private owners. Although environmental awareness does exert a measurable influence on willingness to share and rent vehicles, it consistently ranks behind financial intensive and security assurances in the decision-making hierarchy. This suggests that under current market conditions, green considerations remain secondary to more immediate practical concerns. Despite Greece's pervasive reliances on privately owned cars, with ownership rates exceeding 90% and personal vehicles constituting the dominant mode for daily trips, a substantial subset of urban residents indicate conditional openness to peer-to-peer car sharing. However, this openness hinges on the provision of full insurance coverage, transparent liability arrangements, streamlined booking processes, and robust mechanisms to build trust between strangers. It is important to recognize that our use of non-random snowball sampling constrains the external validity of these results. The sample may not fully capture the socioeconomic and geographic diversity of the broader Greek urban population. Moreover, while our ordinal regression models illuminate the relative weight of economic, environmental, and trust-related variables, they cannot fully account for deeper cultural norms, peer influences, or infrastructural constraints that qualitative methods might reveal. Looking ahead, we recommend that the implementation of real-world pilot programs in selected Greek cities to observe actual user behavior, platform dynamics, and cost-benefit outcomes. Longitudinal tracking of usage frequency, modal shifts, and changes in private car ownership following these pilots would provide valuable evidence of environmental and mobility impacts. Finally, comparative studies across regions with different shared mobility ecosystems could shed further light on how cultural and infrastructural contexts shape the adoption of peer-to-peer car sharing. Thank you very much for your attention.
Brilliant.
Hello.
So that was the recording they shared with us. And I encourage you, if you have any questions, contact them directly. Then let's move on to the fifth presentation titled Understanding Perceived Benefit and Willingness Towards Private Autonomous Cars for Downtown Commuting. And yes, here Fuad is with us. Fuad, the floor is yours. Please share your screen and go ahead with your presentation.
Thank you, Professor Rashidi. Thank you, everyone. Just bear me with a minute to share my screen. And yours.
We can see your screen. Yes, we can see the folder, presentation folder. If you have two screens, possibly you're sharing the wrong one.
Yeah, probably. Just so. Can you see now?
Looks good. Yes, go ahead.
Right. All right. Thank you, everyone, for joining the BTR conference today's session. And welcome you all to my presentation, which is considering the understanding the perceived benefit and willingness towards private autonomous vehicles for downtown commuting. On behalf of my research team, I will be presenting. The research team consists of Professor Graham Curry and Associate Professor Liton Kamal-Jaman from Monash Institute of Transport Studies, Monash University. Now, the main thing in this research is the private autonomous vehicle cars and understanding their private things. Now, driverless cars or the autonomous cars, we all know that is one of the revolutionary things that we have been discussing or researching for last couple of decades. And it is presumed to be changing our conventional mobility concept. Now, the driverless cars, one of the important thing is being discussed in the literature is how they will change our perceived in-vehicle travel time perceptions. And not only that, one of the silent features that the driverless car have is the self-parking capability. And this self-parking capability could actually be cheaper for downtown commuters. In the later of the presentation, I will discuss it more, how it could be perceived towards the user preferences. In terms of the travel time disusability, conventional transport economics theory considers this travel time as one of the cost to the traveler. And as a result, traditionally, all the attempt has been taken to reduce this travel time. Now, AV or the autonomous vehicles could engage people to worthwhile activities, either it's productive or leisure type of activities. And in return, people, if they are engaged into these activities, their value of travel time, or in short, the VOT, could be reduced. Now, those of you who do not know what is the value of travel time, let me just explain you in very short. It is a monetary value that the travelers or commuters are willing to pay to reduce their travel time. So in summary, if the value of time or the VOT is higher, it indicates lower utility and lower benefits to the travelers. In contrast, if the value of time is lower, it indicates higher utility or higher benefits to the travelers. The other feature that we have been discussing is the CBD parking. Now, because autonomous vehicles or AVs have this self-parking capability, according to the Australian Bureau of Statistics 2016 census, we found that 27% of the work commute trips to the Melbourne Central Business District, or in other terms, you can say downtown or city center, were made by car as a driver. Now, city centers or the downtowns are very expensive for parking. As you can see in the screens, the Melbourne, Sydney, New York, Paris, all the downtowns have a huge amount of daily parking cost, which actually makes the parking very constrained for the commuters. During our literature review, we found that private commuters pay these car parking fees either by themselves, which we call self-paid, or their employers pay these car parking fees on behalf of their employees through their salary package, which we are terming as employer-paid commuters. Now, think about is if the conventional private car commuters switch to the autonomous vehicles, they can actually use the self-parking capability of the autonomous vehicles, and they can escape paying the CBD car parking cost, which is significant in amount. And that will have lots of consequences in our travel behavior. So that is the main perception or the main key research in this research project. In the literature, we found that the mood choice behavior for the AV context depends on several factors. It's not only limited to technological influences, it also includes the trip characteristics such as travel cost, driving experience, road condition, parking behavior. According to the US Federal Highway Administration, in peak hour, 1 in 10 CBD car commuters cruise for parking. Now, CBD commuting by conventional private car is highly associated with the parking cost. And research already proven us that if parking payment is paid by the commuter themselves, then 25 to 34% fewer cars would have been driven to work in the CBD or downtown. So it actually, the current literature shows that the parking has a significant impact on travelers' mood choice behavior. But the limitation of the research is no one has actually investigated that how these parking payment characteristics will be impacting the AV mode choice in the AV context. So the research question that we have been going to answer in this presentation is how likely are the CBD car commuters to switch to autonomous cars? To what extent does this likelihood would differ between socioeconomic and trip characteristics? What is the value of time or BOT of car commuters traveling to CBD? And to what extent parking would impact the AVVOT for the CBD commuters? To answer this research question, we have conducted an online questionnaire survey over a period of 3 months from October 2023 to January 2024. We did a structured sampling frame that covers the residential location of the metropolitan Melbourne and also the parking payment distribution. That includes the self-parking and the employer parking. Our targeted respondents were people living in metropolitan Melbourne, or those who drive to the Melbourne CBD by car for work, those who work either full-time or part-time, and obviously 18 years and above. We did a stated choice experiment where each of our respondents have been provided with 5 choice tasks. Choice tasks were designed through engine software package, and we used the D-efficient design method. Finally, we have collected 528 valid responses through the survey. Before going to the choice tasks, we have presented with our respondents with a general understanding of what would be looking a futuristic AV trip with some text and some pictures. The sample of a choice task that we have provided to our respondents is shown here. Now, I'd like to mention here that this choice the choice task attributes that we have provided are 5, and these choice attributes have been pivoted based on respondents' general travel commute time and distances. So these choice tasks were unique for each of the respondents based on their day-to-day commute times. We have analyzed our entire things into 2 stages. The first stage is to understand the willingness for AV commuting, where we have employed the logistic regression model with panel effect for the analysis. Second, we have conducted the calculating the VOT in CBD commuting. We have employed several mixed logic models because of the allowance of the mixed logic models for allowing the unobserved heterogeneity in more effectively. Now, the equations are provided here, but I'm not going to discuss more about these equations. You can find this in the literature as well, or if you have any questions, you can ask me later on. Moving on to our next session. So the first stage, the results of the first stage that I will be discussing here. So what we found here is that at an aggregate level, we found that more than half of the respondents, to be precisely 53.8%, would like to switch from the conventional car to a private autonomous vehicle, or in other terms, private driverless car. In short, we are calling it DC. At a disaggregate level, we find something interesting. We found that the parking payment structure has significant influence on this willingness. As you can see from the graphs here. So as you can see from the graphs here that the self-paid parking commuters have a significantly 60.8% higher likelihood compared to the employer-paid commuters, which is 47.6%, who would like to switch to the mode choice distribution. Moving on to the socioeconomic factors and other attributes, we found 9 individual variables or factors that have significant impact to describe this mode switch behavior. That includes travel cost, parking fee payment, which is the employer paid or self-paid, spatial distribution of living in metropolitan Melbourne, the level of their autonomous or driverless car awareness, demonstration type of the autonomous vehicle through the SP survey, employment status, age, income, and household. What most likely is interesting to find out here that we have done the doing some we have done some graphs here, which shows that if the travel cost is going to increase, the likelihood of switching from the conventional car to the autonomous vehicle also increases significantly. Same as we have found at the place of residence. Now, this is one of the interesting things. Our presumption was that people who lives in the outer suburbs of the Melbourne would be much more willing to convert to the private driverless car, while the inner suburbs, as found from our research, is showing higher willingness to move to the driverless car. Now, we presume that there might be several reasons for that. The number one is that the inner suburb respondents might be highly, they are highly enthusiastic about the driverless cars. Their level of awareness was much more higher compared to the outer residents. The inner respondents were in the higher income group and also having a higher educational attainment, which have an impact on their higher willingness towards moving to the driverless car. At the other hand, similarly, what we have found is people doesn't actually like to have longer commute times, which is a traditional belief in travel economics and the mood behavior theory, mood switch behavior theories. So people always love to have reduced amount of travel time so that they can spend their times into other productive uses, such as spending time with families or relaxation time or other kind of things. So this might be one of the reasons that we found residents of the inner suburbs are more willing to switch to driverless cars. And as expected, the level of awareness, we found that people with moderate to highly aware, they have a higher tendency or willingness to switch to driverless car. To find out that whether the self-paid and employer-paid have any significant distribution, we checked the travel cost variable. And what we found that for the same amount of travel cost, the willingness to switch to the driverless car is 10% higher for the self-paid commuters rather than the employer-paid. And this also be proven in all the other variables, but I'm not going to show all those graphs in here. Rather, we will be moving to the next part of the analysis, which is the estimation of the value of travel time. Now, we have done the value of travel time using the mixed logic models. We have prepared two models, which I'm presenting here. The first model is our baseline model, while the model 2 includes 4 additional variables to capture the effect of parking payment on travel time valuation. Now, as predicted, the travel cost is intuitively negative, indicating that an increase in cost will reduce the likelihood of selecting an alternative. Similarly, the travel time coefficients are all negative, indicating that a disability associated with the increased travel time. But what is interesting is to find out the magnitude of time coefficient, which is larger for the cars rather than the autonomous vehicles or driverless vehicles, indicating that the perceived travel time has more burdensome to the respondents compared to the autonomous vehicle users. Another important thing that we have introduced in our survey is to find out whether the willingness for going for empty cruising, as because we have been saying that parking might be cheaper if they do not go for parking in the CBD rather than they can send it to someplace else. So what we found that the empty cruising for the self-paid commuters is positive, while for the empty cruising for the employer paid is a negative estimates, which indicates that the self-paid commuter has higher willingness towards going for this empty cruising, while the employer paid, they have less indication, willingness towards this empty cruising, indicating they might be going for the traditional way of parking in the CBD close to their workplaces. But in contrast, the self-paid commuters, they can actually escape the paying the high cost of the CBD, and they are higher willing to send their car either back at their home or in between their home and offices for zero parking cost or reduced parking cost. Now, based on this model coefficient, we have calculated the value of time. This table shows the value of time for all aggregate drivers as well as for self-paid and employer-paid. And as we can see here, that the value of time for all drivers in autonomous vehicle is $16 per hour. It is Australian dollar, not the US dollar. And this would be almost 30% lower than conventional car value of time. If we disaggregate it towards the self-paid and the employer-paid level commuters, we find that the self-paid commuters will have almost 33% lower value of time compared to their conventional car BOT. The employer-paid will have a little bit less, 14%, but still their value of time in autonomous vehicle will be lower than the conventional car, indicating that all types of drivers will have lower value of time in their autonomous vehicles compared to the conventional car. Now, what does this actually totally indicate? So we found that more than half of the CBD car commuters in Melbourne, they would like to switch to driverless cars. And parking payment characteristics has a significant contribution towards this likelihood. Now, this likelihood, apart from these parking payment characteristics, it also depends on the level of autonomous vehicle or driverless car awareness, age, income, and household types. What we also found that the AVVOT is substantially lower than the conventional car BOT, and the self-paid parking commuters would be the greater beneficiary group compared to the employer-paid parking commuters in terms of CBD commuting. So what does actually have the policy implication? So if the self-paid car commuters opt for free parking in a AV or driverless car era, that actually includes that there will be a large number of zero occupancy vehicles. And that will also that may increase congestion, emission, and pollutant levels, which will also be contributing towards empty vehicle miles solely for parking purposes during the peak time and off-peak time. The CBD parking demand might drop significantly, resulting in the CBD and downtown empty parking bays. The nearby suburbs close to the CBD may turn into car dumping zone, because as we see, if the willingness of self-paid car commuters going for cheap or free parkings in the nearby suburbs, so that will decrease the road safety and as well as reduce the amenity and attractiveness of the streets. Similarly, and consequently, the parking revenue coming from these CBD or downtown parkings will drop significantly. So local councils and other authorities may have to act accordingly to maintain their fundings and development projects. And finally, the DC and car manufacturers may find it's interesting to find the early adopters of the fully autonomous vehicle driving technology. Based on this total entire research, we have already published a couple of peer-reviewed articles that has been published in several journals. If you have any further questions, you can always email me, or you can ask me in here, or you can also connect me in LinkedIn. Thank you all for listening to this presentation.
Thank you very much for your presentation. I think we have time for one quick question. I don't see any questions in the chat box. So I would say maybe as we transition to the next presentation, still, if there is any questions, feel free to share with Fuad. Otherwise, you have his email and you can communicate your questions and comments after the presentation. Thank you again for your presentation. I believe
Thank you, Professor.
the next presentation, we have one of the co-authors with us, Cheng-Ming Are you ready to start the presentation? The presentation is titled as Assessing the Impacts of Autonomous Ride-Hailing Pricing on Metro Ridership, Traffic Emission, and Accessibility Equity.
Oh, yeah. I'm here, and am I clear to you guys?
Yes, we can clearly hear you.
Yeah, let me share my slide. Sorry. Is it clear to you?
Still loading.
No.
Let's see. Yes, perfect. Go ahead.
Oh, okay. Thank you. Okay. Hello everyone. My name is Chen Ming Yu. Now a PhD student within the Department of Geography at the University of Hong Kong, under the supervision of Professor Jun Xu. I'm here to share our latest work. Its topic is assessing the impacts of autonomous ride-hailing pricing on the metro ridership and accessibility equity. So the background is, so as we all know, the transportation is constantly a large source of emissions within the urban area across many cities around the world. And the metro systems offers low emissions solutions by move large passengers volumes efficiently within the city. But it faces the persistent first mile and last mile problem due to its fixed routes and fixed stations. But another mode, the ride-hailing, recently can help mitigation this limitation by serving as a feeder to the metro station. Let's use the below figure as an example. So if your region, your home is far away from the metro station, let's say like 2 miles away. So if you choose to walk to the metro station, it takes you around 30 minutes to walk there. But the ride-hailing may take you only 5 minutes to reach its destinations. So previous research showed that ride-hailing not only complements metro, like serve as a feeder or serve the underserved areas of the metro systems, but it also competes with it. So the ride-hailing may take you from home to metro stations if you live really far away from the metro stations. But it also may serve as a door-to-door services. So it's parallel with the metro-based modes. It may shorten the travel times. For example, the metro system may take you 40 minutes, and the ride-hailing may take you only 30 minutes. So despite its cost is much higher than the metro systems, so it's also a comparative mode to the metro system. But recently, the maturity of the autonomous vehicles can sharply reduce the operating cost of the ride-hailings, since the driver wages make up roughly on 17% of the total fares you paid for your services. So this means that compared to the human ride-hailings, for example, you paid the driver $10 to cover like 10 miles. So the autonomous ride-hailings may cost us only $3 to maintain the same profit per trips for the commercial companies. So the rest of $7 is paid for the drivers as a commission fees. So the eliminating this elimination of this 17% fees, the 17% gaps, so it enables the flexible pricing for the transportation network companies that prioritize the profit maximizations over the social benefits. So this comes to our research questions is how and to what extent can this autonomous ride-hailing pricing, this flexible pricing, reshape the urban mobility by affecting the ridership, the vehicle miles traveled, and the travel equities across different social economic groups. So to answer this question, we developed a multimodal trip-level framework, integrating the human ride-hailing, the autonomous ride-hailing, and the metro services to estimate the modal splits and the varying ARH prices. And also will consider the travelers' willingness to use the ARH. It's modeled as the function of the prices to reflect the pricing elasticity to the price. So let's proceed to the methodology part. So we select Chicago as our case study for 3 reasons. First, it operates the second largest metro systems in the US. And also this metro system consisting of 8 metro lines shown in this map is designed in the hub and spoke configurations. It means that they all connected in the central loop areas, and also in the peripheral areas, in the suburban areas, the catchment areas of the metro stations is really large. It means that if the traveler residents in the suburban areas want to use the metro system, the access distance and the egress distance for them is really large. So they may need to turn to other modes like the bus or ride-hailing to access to the metro station because they live very far away from the stations. And the third reason is also very important, is that the Chicago asked all its transportation network providers, which means that the Ubers, the Lyfts, these companies to report their ride-hailing trip records to the city of Chicago as part of their routine reporting required by the ordinance. They provide the trip records at the sensor track level and also the fares, the travel times, and also the travel distances, all are public available on their data portal. So this provide us the opportunity to evaluate the impact of this pricing using a trip level framework. So this figure shows the overall workflow of our studies. So we mainly use the three data sources. The first is to use the demand data, which consists of our previously mentioned the TNC trip data is the trip records. And also we use the metro ridership data. The metro is called L train in Chicago, and it's on a daily basis, and it's at a station level. So we need to use the travel survey data to allocate the train, the metro ridership to different sensor tracks to as a OD hourly demand. And the second is that we need to establish the multimodal networks incorporating these modes we want to study. So we use the APIs like the Google Distance Metrics travel time API to calculate the travel time and distances and accounting for the traffic fluctuations within each hour. And then we use this travel time distances and fares to establish the multimodal networks. Lastly, is that if we want to use the route searching algorithm to find the shortest path for each different modes, so we need to convert the travel time to the cost using the value of travel time. But the value of travel time may vary across different socioeconomic groups. So to account for the different value travel times in different sensor tracks, we use the housing price as the proxy for the income to scale the Chicago's average income level, the city level, to the sensor track level. And finally, the demand can provide the OD and the trip start time, and we use the shortest path algorithms coupled with the value of travel time to convert the time to the cost to find the travel attributes of different modes. And finally, we use them to calculate the probability of every individual choosing the different modes and use these probabilities to split the demand into different shares. And I'll specifically introduce the multimodal networks. So from the origin to a destination, they're both on the sensor track levels. So the travelers can use the metro-based modes, but the travelers need to access to the stations from their origin and the egress from the station to their destinations. So they can use either ride-hailing, walking, or bus for access and the egress modes. And they can also use the ride-hailing as the door-to-door services to directly take them to their destinations. So the ride-hailing here can refer to either the human ride-hailing and the autonomous ride-hailing, depending on whether this traveler, this demand accept the ARH or not. And for travelers who don't accept the autonomous ride-hailings, the human ride-hailing can serve as a feeder or door-to-door services for them. And the only difference between these two modes considered in our study is the price. So other factors like the travel efficiency, travel speed, or safety are not considered in this study, in this framework. And next, I introduce the experimental scenarios of this study to examine the potential impacts of the ARH pricing and their adoptions. We explored a set of scenarios by varying two key factors. The first is the price rate. It's defined as the relative price of the autonomous ride-hailings compared to the human ride-hailings. You can understand it as a discount offered by the autonomous vehicles. And second is one is the traveler's willingness to use ARH. For the first, let me explain the first definitions. So, for example, if the ARH price rate is 0.4, it means that for human ride-hailings, it may cost you 30 minutes to reach the destination and $10. So the autonomous one only costs you $4. So the $6 are the differences between these two modes. And a previous study shows that the traveler's willingness to use this mode can increase it with the decrease of the ARH prices. In this service, in their surveys, around 3,000 respondents. So of €3 fare reductions, which is equivalent to 20% of 22% of the original fares of the human ride-hailing fares, can result in a 20% increase in the respondents choosing the ARH services. So we use this linear relationship to create a set of scenarios for this study. So the price rate is varied from 0.9 to 0.4. So 0.9 means that the autonomous vehicles, the cost saving from the autonomous vehicles is only about 10%. And we also calculated the willingness to use these modes. So it's varied from 0.41 to 0.86. So let's proceed to the results part. The first is to validate against the real world values. So we calculated our estimated values as we plotted the scatter plot of our estimated values versus the observed values for the ride-hailing shares and the real world VMTs. So in this scenario, there is no autonomous vehicles. So there is only human ride-hailings in this scenario. So the deviations shown is from the real world values are negative 6.77% for the ride-hailing shares, and also a positive 16.51% for the VMTs. And these deviations may stem from three perspectives. The first is the travel time distances are calculated using the APIs, not the real world values. And the second one is the calculations are based on the locations of the sensors tracked, not the exact coordinates, because these are the most resolved spatial units in your study. And the third one is other factors like acceptable factors other than the time and the cost, like the comfort and other perceptions are not considered in the distributive functions in this study. But the R square is both around 0.7, and the reasonable deviations indicate the validity of applying our framework for further investigations of the impacts of the price raise. So this figure shows the effects of the price raise on the model shifts. So the figure 5A shows the mode shares of different modes at different price rates. We can see that the orange bar represents autonomous ride-hailing shares. It increases as the price rate decreases, and the other mode shares both decreases. This means that the ARH, the autonomous ride-hailing, is shifting riderships away from the human ride-hailings and also the metro-based modes. So it's taking the whole ridership. And we also, from the figure B, we also quantify this by fitting quadratic functions. We can see that this effect is actually not linear. It's a line linear shape. So the ARH, the orange line, so it follows a convex accelerating trend as the price decreases, and the metro-based modes, metro plus other modes, also decreases accordingly. And lastly, we show the probability of choosing the ride-hailing at different travel distance and under different scenarios. So we can see that all these 4 lines at different price rate in different scenarios decreases as the travel distance increases, since the longer the travel distances, the higher probability of the users turn to the metro systems. But at a lower price, let's see the the purple lines. So the declines flattens as the price decreases. So this both results in a larger quadratic coefficient of the VMT. This means that at lower prices, lower price rates, the VMT increases more disproportionately than the ridership. And we also evaluate the effects of the price rates on the cost and accessibilities. The accessibility measure here is just simple the weighted travel time at different sensor tracks. We can see that these are the lower prices can reduce the cost and also the increase the accessibility, which means that reduce the travel times. But these effects are also nonlinear, but they are more modest than the effects on the ridership and the VMTs. But it doesn't mean that this advantage is offered by the autonomous ride-hailing offsite are outweighed by the disadvantages. It means that we need to carefully balance the advantage and disadvantage to regulate this market. And we also evaluate the effects of the price raise on the travel equities. So we geo-cluster the sensor track based on their the income, the demand, the access distance to the metro stations, and the wide proportions to divide the city of Chicago into 5 groups, from group A to group E, from the most advantage, socioeconomic advantage, to the least advantage. As you can see that the average income decreases from A to E, and the average access distance to the metro systems increases, and the wide proportions also decreases. So as you can see that group A and B are the advantaged areas, and the group C and D and E are the disadvantages because their average income are below the city's average, and they are not white dominated groups. And we calculate the accessibility gaps and also the travel cost gaps under different scenarios at different price rates. And the scenario 1 means that the gap between the most and the least advantaged socioeconomic groups means that the gap between A and E, and 2 means the gap between the advantaged groups and the disadvantaged groups. So we can see there are significant gaps between these advantaged groups and disadvantaged groups. And as the price rate decreases, as the costs of the autonomous ride-hailing fares are lower, so these gaps decreases, and this trend is significantly, which means that the lower price can benefit the disadvantaged groups more than the advantaged groups to help narrow the gaps and improve the travel equity. So let's conclude this study. So we present a triple-level framework that integrates the human ride-hailing and autonomous ride-hailing and the metro services to evaluate the effects of this pricing in a multimodal network context. And our findings reveal that first is lower the prices, resulting in a linear increase in the demand and also the vehicle miles traveled. And this growth is mainly driven by the shift away from long-distance metro trips. And the fare reductions also can improve the accessibility and ease the cost burdens for the especially in the disadvantaged areas with limited transit access. And these results emphasize the need for the regulatory strategy that balance the advantages and disadvantages of these emerging mobility systems and guide them towards a broader urban policy objectives. I think that's it. Okay, thank you.
Thank you very much, Qingming, and very interesting study and great presentation. Let me see if we have any questions here. No, we just have another session following this session. So if you have any questions, please reach out to Qingming. And I hope you enjoyed this session. It was very interesting, and very interesting presentations were shared with us. And if you're interested in other topics, in 10 minutes, we have other sessions, parallel sessions happening. Thank you very much, Yikang, for your help.
Thanks, Taha.
Everything
I'll
went
share
very
reading the session.
smoothly. Thank you. Have a good day, everyone.
Thanks.